Glad to be here today. I'm actually pretty excited amongst the many presentations that I've done at the Banff conference. This one here in particular, I'm pretty excited about. So can you guys hear me in the back? I know I don't have a mic and you're good? Okay. All right. Okay, we're gonna jump into it. Other direction. So just a little bit about us for those who don't know. AWWOA's been around actually for over 70 years. And we really focus on developing technologies, natural processes to enhance treatment. And that's essentially what we're going to be unveiling today is a new technology we've been working on. And this new technology, we've been looking at solving this issue around phosphorus since 2016. Because we hear from you when we talk to all of our clients across Canada and the US, we hear issues, we understand problems, and then we try and internalize and see what we can do to make something else. And this is a good example of how we've taken an issue, and more so not even in Alberta, it's in the rest of the country, and I'll get into that, and then how we then apply it to a new technology. So just as a review, this is the backdrop of what we're talking about. Phosphorus is a pretty big challenge. We all understand when you have high amounts of phosphorus, you have algae blooms, and we have degradation of all the aquatic life, rivers and lakes. Why this is such a big deal is that phosphorus doesn't gas off like nitrogen, right? It's a macronutrient, means it just stays, it does not easily break down. That's why most wastewater plants have major issues with disposing of it, and that's why the limits on them are so low, is because we don't want phosphorus entering the waterways. So these are the limits, the regulatory requirements, milligrams per liter across the country. And the interesting part here, I'll talk more about Alberta, but you can see it ranges. Manitoba is the most strictest requirement, and almost every single system in Manitoba has a requirement as part of their permit to remove phosphorus. But in Alberta, there's actually only about 40 sites that have phosphorus limits. They're looking to increase that, and more so they're focusing in on very targeted areas where the watersheds are really critical, where the addition of phosphorus to those watersheds will make a huge impact, and so they're going to start there, but they're going to be expanding, and I can see in the next 5 or 10 years, everybody having one. Because in Manitoba, Ontario, BC, everybody's got one. Saskatchewan is similar boat as Alberta. There's just a few sites that have it. And I think it's just taking time to get to the central part of of Canada. Because all those other areas are all connected to major lakes, major bodies of water. And so eventually it'll come here and we're gonna have to find a solution. Because as you'll see here, biological and chemicals are not the best way to go about it. So biologically, you need living organisms. That's actually where AWWOA's primarily in, is biological. So we know the weaknesses and the strengths. We know what shortcomings are there. And as you know, as I just said, phosphorus can't be consumed by bacteria. It can be consumed by bacteria, and they do consume it. But then they die off, and then after a time it re-releases. So phosphorus biologically has to be removed through the sludge on a regular basis. And so most wastewater mechanical plants have activated sludge, and that sludge is coming out on a regular basis so they can strip out that phosphorus. So that's how the biological process works. But on a lagoon system, if you have bacteria and enzymes in there, it can help capture the phosphorus, but it settles, and then it releases later on. And so all of the systems in Canada, I remember about 14 years ago not hearing too many people having algae issues. 14 years later, a lot are. And that's because phosphorus is now accumulating over and over, year after year, and staying within the system and not leaving very quickly. So in Ontario, they use chemicals, which is the next one, to precipitate it out. They'll use alums, coagulants, whatnot. They'll all add it into their ponds, and there's actually so many more lagoons there than there are here. And they add that chemical in right before they discharge. So it helps bind the phosphorus, but when you use alums and coagulants, it increases the volume of sludge, and that volume of sludge then goes to the bottom of the lagoon, at which point then it has to be manually removed. So chemical precipitation works great if you have a huge wastewater plant and you're able to strip out the sludge on a regular basis. And then they use more alums to then de-water it again and dispose of it. But the issue with the big wastewater plants is the chemical costs are higher and higher and higher. And on top of it, it impacts the water as you use it. And so we're going to try to minimize impacts, but still solve the problem. So you can see there are some serious issues. If you use chemicals, it's severely higher amount of biosolids. It consumes alkalinity, which means you can have various swings of pH. And then you have expensive budgets for manual removal. And both the chemical and biological process tends to have larger footprints. So then it's real estate, and then major acquisition costs and infrastructure costs to be able to facilitate either of those processes. So that's why we're trying to think about, is there a method where we can downsize it in a smaller, more compact area and able to strip out the phosphorus? We need to actually remove it from the water. And that's where the Vortex comes in. Vortex stands for electrical chemical oxidization. So there's three main parts to this. So there's the coagulation part. What happens is it requires electricity. That electricity then reacts within our cells, which I'll show you a video in a second. Then when it's in those cells, it releases these ions that are able to bind. You're able to have faster reaction times within minutes and seconds rather than biological length of time. And then also, it's not sensitive like biology. Biological processes are quite sensitive to temperature and other conditions, like alkalinity. So that's why it's able to be able to have the benefits without the limitations of biology. The whole point is to try and lower operating costs, not reliant on chemicals. Right? we normally get atrazine normally gets put into the chemical category, but it's a natural process. Again, we're all focused on natural methods and ways to be able to remove and solve wastewater treatment processes without having to have major costs. For some reason it's cut off here, but essentially the electricity will be replacing the chemical bulk usage of chemicals. Right? We can design systems that can handle not just phosphorus and ammonia, but all sorts of other things as well. This is just the first target that we're targeting because phosphorus is so prevalent and everywhere. So we're going to be looking to expand different, other metals, other things in different areas, manganese and other things, but phosphorus is the main one that we're going to be focusing on for now. So our whole grant, our whole process started about about a year and a bit ago. We started contacting Alberta Innovates. They were able to grant us some funds for this project. That happened in September. The whole length of the project is 12 months. These first few months was the development of the system. So we custom designed our complete whole system. But again, we've been doing the research for many, many years to try and do this. Because we had a pilot at the beginning, a really small scale one, and now we're at a full scale system. And so that's the first part, is that 12-month process. Then we're going to be going to Crow's Nest Pass and to Flare. And at Crow's Nest Pass we'll be doing the wastewater, and Flare we're doing water. And it was brought to our attention that wastewater is not just the only place that deals with phosphorus. A lot of water, potable water treatment, requires treatment. They're receiving from a river that is more polluted than the water they want to discharge. So they're using chemicals to deal with the phosphorus, chemicals to deal with any type of organics or suspended solids in there. But then when you use those chemicals, they react with the water and cause other side effects. You need other chemicals. And so the one in Flare, two times a year, they use up to 8 chemicals to be able to send water out and distribute it. So there's so many things there and balancing acts that have to be required. So if we can strip out those organics and phosphorus beforehand, that'll be an easier process for them. So this is a little picture of the inside here, but there's electrical coagulation, and I'll get into that, electrical oxidization. We're using the process called ion exchange. It's a well-known process that when ions from metals are released, they then bind with what other, if it's a negative or positive, right? So if they create this positive charged flock, then they will bind with anything negative like phosphorus. Then we have also fine filtrations. It's going to be chemical free. And then we're going to focus on a compact modular design. This is the little short, like 30 seconds. This is just a little tour so you can see what it looks like. So the front of the control panel. In here are 24, two different phases of electrical cells. And all of our rectifiers and control panel and breakers. Those are all the different 12 cells. And this is the opposite side where the electrical side is tied into all the anodes and cathodes in every single one. And then we have two micron filtration systems that's able to then strip out everything that goes in beforehand, as well as the reaction takes place. And it all fits within a 40-foot container. So, phase one. Phase one is the most important, which is the electrical coagulation. Sorry, I've gotten a cold recently. So we have an electrical current that then goes from our rectifiers into each individual cell. It goes through the metals, reacts with the metals, releases ions into it, and creates those flocks. Then those flocks are able to then bind with the phosphorus. And they bind and develop an insoluble phosphorus solid, which is called pit flocks. Tiny little things that then are able to be filtered. And that process is way more efficient at removing phosphorus and as far as volume as well. It's like 80% less than chemical usage of alum. And so the amount of sludge produced from this is minimal compared to any other process, as well as more efficient because it attacks we're basically producing the same type of effect that polymers would create, but without chemical. We're actually creating it in situ inside of every one of the Vortex cells. All of this is done through it. Then at the end of it, as these electrodes function, they also produce micro bubbles releasing oxygen and hydrogen, which then move the process along and move those particles and those flocks attached to the phosphorus, and they move those out through the system for filtration. The second process, the other 12, is electrical oxidization. This is where we're generating reactive oxidizing agents to actually break down and destroy organics, as well as E. coli and other harmful pathogens. Right? It goes through these pipes, through the process. It actually creates hydrogen peroxide naturally in the system, basically cleaning and sanitizing the water after the first process. There is no reagents added, so you don't have to add any kind of peroxide to it. It actually creates it through our custom design anodes that we've developed. And that way, then it also, when it has these oxidizing agents, it reacts with nitrogen and is able to reduce nitrogen. Those are the two main processes. In between those are all the filtration. So we send the water through the first filtration to remove 2 microns of everything. So before it even hits the system, it's already pretty cleaned up. Then after that first process of electrocoagulation, it goes into another the same filter, but like another pass to remove out all of the phosphorus as much as possible. Then from there, it goes to the second process for oxidization and sanitation of the water, and the final oxidization of the ammonia and BOD. Then it goes to the last step of the filtration, where the remaining TSS and any other phosphorus that hasn't been removed in the first stage will be removed at the very end. So why is this unique? Or why would someone consider looking at this? Is nothing else out there actually exists like this. This is bringing multiple different technologies all within a very compact process. So it's compact, able to produce all 3 of the main things: electrocoagulation, electrical oxidization, and fine filtration. Again, all within a 40-foot shipping container. which hasn't ever been done so far. And it's all because of the specifically designed components that we've developed that are able to react with electricity and provide the solution that we want. So we went through and developed a comparison of all the other technologies or the methods of dealing with phosphorus, right? So you have your lagoons, your enhanced biological phosphorus removal, and then your membrane bioreactors, and those are the main ones on the market. And as you can see here, the cost is actually right in line as one of the cheaper alternatives. And this is over a 10-year life cycle and per cubic meter. So it's a very fair comparison when you break it down per cubic meter. But even with that aside, when you move on to the next things, this footprint is really small. This can be added to any process in any system when it wants to have that final polishing process to remove phosphorus and the last bit of organics and ammonia. Right? No chemical usage. It's actually also not sensitive. You don't need to be as sensitive like biology in the reactors or the lagoons. Right? This actually happens directly. So there's no, it could be in cold weather, it could be warm weather. It's all electrically controlled through current rather than the biological activity. The sludge, also as I already mentioned before, is the lowest of all of them. Right? And we already know how difficult it is to remove sludge. All the permitting, disposal, transportation is all dropped down significantly so that you don't have to do as much with sludge. And then at the end is the energy consumption. In lagoons, you don't think normally energy consumption, but that's based on aeration. As most lagoons are required for aeration in other provinces. Alberta is not like a major requirement. BC is like mandatory. But more and more are saying that you have to add on aeration to your system if you don't currently have. When your permits and stuff renew, that's an often large recommendations to add that on. So when you compare it against that, then it's still cheaper than aeration. But then it oxidizes all the water and strips out the phosphorus and ammonia more efficiently than the aeration would, and as well as adding all the chemicals to do it. So as just a review case, so the process is it has to be located after some kind of primary settling. Right? The system's not designed to take on all of the heavy sludge at the very beginning. The heavy sludge at the beginning would be too difficult to handle, so you just put it right after, like if you have a lagoon systems, it could be after anaerobic cells, or if it's a wastewater plant, it could be after the first primary clarifier, where the original solids are stripped out. This can then handle the rest of the part. Or it could be done at the very end of a process to discharge through, or recirculated at the very last cell just to strip out phosphorus completely. And these are some of the expected performances based on the results we've had so far. So what we've done so far, like I said earlier, we've had smaller versions of these to do some different prototyping. And that prototyping has allowed us to get better and better results. Just so you know, always taking pictures. Keep going. I have a link, a QR at the end. If you want the presentation, I'll just send it to you. Plus any other updates or whatnot too. So main goals, phosphorus, right? Then COD, E. coli with the oxidization process, and then removing ammonia through the oxidization as well, turbidity. So it's not like complicated, the process, but it's very more sophisticated and took us thousands of hours of design to custom develop the anodes, electrodes, the vortex cells, and understand how it all functions and works together. And so we're excited to get it out and get it ready. So we're hoping to start the trials end of May, June in Crow's Nest. And then after that, we'll be up into Flare. And then we're looking for other sites in Alberta that want to try, and more pilot sites as well. So the impacts on water are pretty self-evident. If you can remove phosphorus at a high level, high percentage level, then you won't have algae. If there is no phosphorus, there is no algae outbreaks. So we can remove it. If it just sits there and runs consistently at the end of one cell and recirculates the water through, they'll just eventually take all the phosphorus out over time. Right? reducing chemicals. Right? I'm of the opinion, always have been, that we want nature to be natural. We don't want to keep on adding non-natural, non-biological things into the environment. And we want to be able to do so and not impact the quality of water we have. And I was just chatting earlier, we have some of the best water in the world in Canada. So we want to make sure that we maintain it as best as we can. Be good stewards of our water. It maintains a healthy alkalinity, right? This will meet all regulatory requirements. And then it will obviously protect our watersheds. So here's some actual data. So this is the data that we again, this system was a lot smaller. It was designed for just to test out the process that it could function. We went to a greenhouse because we thought greenhouses have a lot of phosphorus. And their phosphorus is at 32 milligrams per liter that they were discharging. And the city was like, we don't want you to be discharging 32. We want you to be, crazy enough, under 10. Because it was concentrated, but not massive volumes compared to the whole city. But they still wanted it to be under 10. So I'm like, man, we can hit that mark. We can get underneath 10. So we set up the system. We went, because the system itself was designed to only remove, the original one was around 2 or 3 milligrams per liter. And so this one's 32. So we had to circulate it through a few times to be able to get the full 32. It's about 6 or 8 times it went through. And we were able to get it down to 1 milligrams per liter. So it removed the phosphorus, it reacted, and that picture before, those flocks, that was the end result from there. It just bound with that phosphorus and was able to easily filter right out. So this was like a second prototype where we took even more stronger wastewater, more municipal raw wastewater, and then took it through about a 2-month period of before and after with BOD, effluent, and this is again after that first primary settling. So right after the first, it still had significant BOD and TSS, and was able to get all, which really extremely good numbers, through one pass through our system. So if we wanted to have even better, you could repass again. So we've been able to optimize this, automate it, and be able to control recirculation so we can adjust how many times or it needs to pass through or to hit a goal that we want to have for treatment. So what are the byproducts? What does this produce? So that's one of the big things is we want to know what kind of other impacts does it make. So the two main byproducts is the phosphorus. So this is the rolled media. This is the media that comes out of our system. It's not a filter, like fixed filter. I think it was fixed filters. There's backwash, and then you have to deal with backwash, and that has all the phosphorus. So it's like, so we were able to develop a system where we have rolled media that comes out, and all the phosphorus, ammonia, and TSS ends on this. So that has to be discharged or sent to the landfill on garbage. But we're already working with to develop a new filter that's actually all fully organic. So then it can be composted and beneficially reused. Because this is going to be really high in nutrients. And so that's not our main priority right now. We know that's a really good extra benefit that we can do, but my main focus is on just removing it. And this is going to go to landfill for now until we develop a filter that can do that. And then obviously the other byproduct is the water coming out. So as it comes in, we filter, go through the process. As it goes out, it's treated. And the only other discharge is the paper that is just put in the garbage and disposal. This is what we're going to be measuring. If you can think of anything else we should measure, let me know. Because again, we want to have all of our data information totally bulletproof. If there's something you're like, oh, you're not forgetting this, or something else. But this is what we're going to collect at least 3 times a week from a lab at our pilot sites. But we have continuous monitoring of phosphorus and ammonia, or phosphorus and nitrogen, which is continuously grabbed. So we'll know and be able to make adjustments on the fly of how that's working. Because again, those are the ones that we're wanting to hit. The rest of this will just be grabbed and sent to a lab. So then we'll be able to third-party verify the lab data that we're receiving in the actual system. So I just want to show you like kind of our step of how we kind of changed. One of the biggest problems is trying to take an idea and make it into reality. Trying to convert something that might work at a small scale in a lab to actually full scale. So the learning is crazy, and the hurdles, blockages are like innumerable. It's like I get one every single day. I just talked to someone I'm working with, and he called me right before this. I'm like, guess what? I'm like, okay, thanks. So one more thing to learn from. So we started earlier with lab scale stuff, then we went to around 300 cubic meter per day, and only around 3 milligrams per liter. This is the one that's going to be used in our pilots here in Alberta. So I can do up to 1,000 cubic meters a day, with around 14.8 milligrams per liter. And I was thinking more of the greenhouse, so if I could have it just through 2 passes, I could still clean up the greenhouse better. With this, most municipal wastewater plants are way lower than 14, so that we can adjust our flow and still reach the objective target that we want. And so it's all fully automized. The previous one wasn't automized. Again, we don't want to put all the money in the first prototype. So we spent all the money on this one because now we've learned so much from between the two. So now we have those 24 mini Vortex tanks. Everything's fully automated. It's going to be sent to my laptop, all reported, all data, so I can optimize and change any parameter that I need to, so that we're able to maintain treatment or just experiment with it. And like, what if I do this and that, and how do I max this out and max this out, and so I can actually understand what it could be done. So there's the system on just the one. And this phase here is phase 1, and then phase 2 of the different chemical reactions that take place. There is an electrical requirement. That's the max of what it is. And that's like, again, everything electrical has to at least be 30-25% above what you're actually even going to plan to use. So we're not using close to that, but that's how we're planning to receive the power. Some of our next steps: full-scale deployment, which is coming in the next few months, collecting all the data humanly possible, and looking at multiple sites. So if you know of a site that might be having issues with phosphorus, or actually has a permit, or being told they have to do something, we want to try and prioritize those that have a more urgency. We'd like to talk about that. And then we'll start looking to the ongoing maintenance of it, the ongoing cost of running and managing it. We have a pretty good idea, but real life, again, is completely different than the lab, and so we'll be working through that. Here's the QR code if you want to scan this. You just put your name and number and email, and we'll send you information, keep you up to date on all of the details of everything. Or if you're interested in being part of a pilot for our continuing education on this. Again, this is such a huge learning process for everyone involved, because we're trying to create a very novel new technology to solve a very particular problem. So with that, thank you for coming and participating.